Welcome back. Today we're doing problem 189, rotate array. I actually got a mic now, so hopefully the audio sounds a little bit better. If not, well, that sucks. But, okay, so given an integer array nums, rotate the array to the right by k steps, where k is non-negative. So let's go through the first example. Nums is equal to this list up to 7, k is equal to 3. That means they want us to shift everything in this array over to the right by 3. So your output would be 5, 6, 7, 1, 2, 3, 4. This explanation is actually pretty good because it goes step by step. When k is 3, you have to rotate 3 times. So the first rotation, you can see 1 moves over to the right once, and 7 doesn't just fall off, it comes back over to the beginning of the array, right? And you rotate 2 times, 7 comes over another time, 3 times it shifts over another time, and all of the numbers before it also follow it. So finally you have 5, 6, 7, 1, 2, 3, 4. The second example is pretty much the same. K is 2 now, so we're only shifting over to the right twice, and there's 4 items in here. So you can see here that -1 ends up 2 positions over from where it originally was. And finally you have 3, 99, -1, and -100. So there's a couple different ways to do this problem, but let's move this over here. It's asking us, can you do it in place with O of 1 constant extra space, right? Great thing to do is just try to do this problem however you can in the first place, and then we move on to this constraint here, right? So we're going to talk about our first approach, and let's do that here. Let me move this over. And so to solve this without ignoring our space constraint, right? Our space, why isn't this going, oh shit. Why isn't this going away? There we go. Ignoring the space complexity constraint, let's just try to do this however we can. And the way that we're gonna do that is we're gonna use a separate list, which I'm gonna call output, and it's the same size as nums, and it's actually going to be just filled with zeros. It doesn't matter what this is filled with, but I just fill up with zeros. And what we're going to do is, the basic idea here is we're going to loop through nums to figure out where to put each individual number after we've shifted it, right? So we're going to do that calculation for every number, 1, 2, 3, so on and so forth. The difficult part here, right, is figuring out, okay, where do I put this number, because it's not as simple as just moving it up by 3 positions. If I am at position 0, 1, 2, 3, 4, and I'm the number 5, I can't just move up 3 times because then I would be out of bounds of the array, right? This is an array of size 7. I can't be putting things past the edge of the array, so I have to loop back to the middle. So how are we going to do that? We're going to use the modulus operation, and I'll show you how that's going to work exactly, but let's just go through this basic chunk of code that's going to walk through how this is going to work, and we'll trace it. But this loop is going to go from I through nums, so I is going to start, oh wow, beautiful, at 0, right? And k is always 3. Remember, k is always 3. That's how many times we want to shift over to the right. Our position is going to be I plus k. So in this case, it's going to be 0 plus 3, which is 3, modded by the length of nums. This never changes. This is always 7, right? And so it's going to be 3 modded by 7. What's 3 modded by 7? It's just 3. When you look at the modulus function and how it works, any number modded by a number larger than it is always going to be whatever number you want it on the left side, right? Because there's no leftover, or there's no leftover, yeah. So it's 3, and so our position now is 3. So output at position, which is 3, this index, is equal to nums at I. Well, I is 0, so nums at I is 1. So now we know where to put this 1, right? 0, 1, 2, 3. Here. We're going to do the same thing for the next iteration, right? I becomes 2. Sorry, I becomes 1. What am I doing? I becomes 1. And when I becomes 1, position is now equal to 1 plus 3, which is 4, right? And when 4 is modded by 7, you get 4 still. So now we know that the position we have to put into our output is at position 4. And what are we putting into there? Nums at I. Nums at I is 1. Sorry, I is 1, so nums at I is 2. So at position 4, we're putting the number 2. This is gonna keep going, like 3, and this is 4. But then now let's look at this case here, right? 5. This is the interesting case where things get like the modulus function is gonna make more sense here. So let's actually walk through what happens, right? So at this point, 0, 1, 2, 3, 4, I is equal to 4, right? We are at element 5 inside of nums, so I is equal to 4. 4 plus 3 modded by 7 is 7 modded by 7. Well, 7 modded by 7, there is no leftover. It's 0, right? If you're confused about this, go look at modulus and how it operates. So our position is at 0, so we've looped back over to the beginning of our list. And then output at position 0 is equal to nums at I. Well, I is 4, which is pointing to nums at 4, which is this value 5. So we're going to fill this up with 5. And then you're going to keep going. So when later, right? Oh my lord. I is 5. This is now 5, which is 8 modded by 7. Well, the leftover is 1, right? 8 modded by 7 is basically, think of it this way, like 8 divided by 7, but there's a leftover of 1. So at position is now 1. Output at index 1 is equal to nums at I, which is, why did I put a 1? 6. And then we'll do the same thing again, we'll get 7. So this approach, this super messy approach, it's not that messy, this will solve the problem. But now let's talk about it in a way where we don't use extra space complexity, yeah? And so the way that we're going to do this is, the question is asking us to shift over to the right. An equivalent way of saying shifting right is moving k elements from the right to the beginning of our list. So I'm going to say that again because that understanding is really important, right? Seeing things in a different way, at least for me. So shifting elements to the right k times is the same as moving the last k elements, right, over to the beginning of our list. So how are we going to do that, right? The approach that we're going to take is, it's actually very simple and the code is really short. What we're going to do is, I'm going to make a copy of this. We're going to we're going to loop k times, right? We're going to manipulate the list, the array in place. We're going to pop from the end of our list. Oh my lord. and we're going to insert back into the beginning of our list k times. So we did that once, right? Now we pop again. We insert back into the beginning. We've done that twice. Pop one more time. Finally, we're done. And this is the output that you should have. 5, 6, 7, 1, 2, 3, 4, right? So the idea here is loop k times, pop each item off the end, move it to the very front of your list, and by the end, that uses no extra space, and it actually is performed faster because you're only looping k times. So let's get into the code, which is, I pray I don't mess this up because it's really short. So for I in range k, right, we're going to loop k times. I'm going to say shifted number equals nums dot pop, and we're going to pop off from the right side, remember, because we're taking this value, this 7, we're going to move it, we're popping this off, removing it, moving it to the front, yeah? So that's what this is, and now we're going to insert at the very front, so position 0. I'm going to zoom in a little bit here. Okay, I regret that. I lied. And we're going to insert our shifted number. So that should be it, I think. Nice. Great. So the runtime for this is actually O of k, because you're looping k times. Worst case is it's actually k is n. Oh, actually, k can be larger than n. So actually, yeah, this is going to be O of k, right? You're going to do this k times. You're going to keep shifting, popping, and it uses no extra space. So space complexity is O of 1. Great.